Greetings and welcome to another exciting lecture in geomorphology. The topic today is going to be hill slopes. That's right, we're going to be talking about hill slopes today. And so that's our plan for the entire lecture, is to talk about kind of the different forms of hill slopes, what they look like, how climate plays an important role in kind of the overall shape of a hill slope and how much sediment is on that hill slope. And then we'll talk about starting to quantify some important aspects of hill slopes through the concept of shear stress, shear strength, and angle of repose. And it's going to allow us to start thinking about slopes that are stable and slopes that are not stable and the likelihood for mass movements. Now, we'll get into different types of mass movements next week in our next lecture. But right now, let's just start with those hill slopes and hill slope forms. So just showing some nice pictures here to start off of some beautiful slopes around the world. You can see just kind of the variety of slopes that we see. Some that are covered in bedrock with minimal vegetation, and then others with lots of vegetation on. Okay, so a term I want to just introduce right off the bat in terms of a form of a hill slope that we see particularly in arid regions is what we call a dip slope. Now, a dip slope is where the actual slope of the hill is determined by the underlying bedding. And so as everyone see here, this is my friend Kevin. He's giving a lecture on the sedimentology here associated with these Cretaceous beds. That's a different story. What I'm talking about is, notice here that we've got a slope coming right down the side here that is at the same angle as the bedding. So we call this a dip slope. So here we're looking at some Cretaceous units again, and you can see this whole layer right here. Does everyone see this? And so we've got a sandstone on top of it, and the actual form of the hill slope is related to the underlying bedding. So here we've got a nice example here again of some tilted beds, and look at this. You can actually see this is a sandstone, and it has bed form patterns on there. We've got wave ripples on the sandstone, and the hill slope itself is basically the bedding plane itself. So that's what we call a dip slope. Okay, next up I want to talk a little bit about kind of how we see different types of hill slopes around the world and how that's related to climate. And so in more arid regions, we have hill slopes that are dominated by bedrock. And if you look at this picture here behind me, right here, see these hill slopes? There's not a lot of vegetation on them. And so we call these weathering limited hill slopes. Now, what that means, weathering limited, that what's controlling the form of the hill slope is the fact that weathering rates are low relative to erosion rates. And so any material that's created on the hill slope is kind of flushed off the hill slope. And so the form of the hill slope is mostly bedrock. We call that weathering limited. Okay, so landscapes in the desert Southwest, like we see here in San Ysidro in central New Mexico, are classic examples of bedrock-dominated hill slopes where we have, when weathering does occur, it's dry in the desert Southwest, so we don't have much weathering, and when we do have big rainstorms, we can flush that sediment off hill slopes. We end up with these bedrock-dominated slopes. Okay, moving along, kind of our gradient here is, if we have what's called low gradient slopes, so kind of at the top of a slope, we might see more vegetation. We might be trending towards a slightly wetter climate, and we end up having what's called a low gradient interfluve. What that means is it's a higher surface that's in between a fluvial valley down below. And so we call these interfluves that are sitting above the active where we would have fluvial processes. All right, if we flip to the other side here, we end up with convex hill slopes that we see in more humid climates. And so here we call these transport limited, that because we can do more weathering, we produce more material on the hill slopes and we can't transport it off. So we're limited by our ability to transport the material off the slope. These are transport limited slopes, and we see these generally in more humid climates. Okay, as we kind of progress down to the bottom of the slope, or sorry, another term here, we call these soil mantled slopes. So soil mantled slopes, transport limited. So here, not a lot of bedrock sticking out on this hill slope, right? Okay, as we move down to the bottom of these, we get what are called the lower toe slopes, or the concave part of the slope. So the top of the slope in humid regions, we call that the convex part of the slope. It's convex. And then as we start to stack up sediment on the base of the slope, that slope gets more shallow, and we go from convex to concave. And at the bottom of the slope here, we end up with material that's accumulating and thickening on the bottom of the slope. Okay, excellent. Another term I want to introduce that's really important when talking about hill slopes is colluvium. Now, colluvium is material that is really just broken up bedrock that's just sitting on the slope. It's recently been generated. It hasn't seen a lot of transport. And I've got two pictures here of two examples of thick versus thin colluvium. This first here, this is from Wallula Gap. And then here's bedrock right here, and we just have a little bit of colluvium on top. Then my picture of thick colluvium here, we have meters and meters of colluvium with well-developed soils that have formed here on this thick hill slope deposit on a hill slope in the Sandia Mountains of New Mexico. So here is a kind of a schematic here of how we think about colluvium. It's often thinnest along ridge crest and then thickens as we go down hill slope. So that's kind of colluvium. I'll be using colluvium a lot. Okay, so that covers our basic form that we see in hill slopes. And what I want to talk about next is basically how we can start to understand quantitatively how these forms exist. And so a really important characteristic of rocks and soils that we need to talk about is the strength of a material. And so when I talk about strength, I'm talking about how a material resists deformation. That's the strength of the material. So there's different types of strengths with any given material here. So here I've got a pen. And so I've got a pen, and this pen has a certain amount of strength to it, and I can try and break that pen. You could try and push it together, and you would push, push, push. That would be a compressive stress that we're putting on it, and a compressive strength, how well it resists deformation when you squeeze on it. And then the opposite of that would be tensile strength. As you're pulling something apart, how well does it resist our ability to pull it apart? Now, I used another term here that I want to introduce, and that is strength versus stress. So stress is essentially the force that we're putting onto our object. So force. Okay, let's take a quick break here. I'm going to pause and we'll come right back. Okay, sorry about that. And we're back. And so we're talking about strength versus stress. So a stress is a force applied to an object and over a certain area. Force per unit area is a stress. So I can apply a force, say, to my hand, okay? So I can punch it, right? And then the force would be how hard I'm accelerating my hand towards my fist. And then the area of my fist, if I multiplied by that, I could get or divide by that, excuse me, we could get our force per unit area. So that would be our compressive, or excuse me, our stress that we're applying to my hand. Now, my hand has a certain amount of strength to it, right? Before it would deform. So I can punch it, and as long as I punch it and my stress is less than the strength of my hand, nothing happens. Now, if you punch it really hard, you have bones in here. Your bones are only going to have a certain amount of strength to them. If I exceed that force in my stress, then I'm going to break them. So does that make sense? The strength versus the stress of a material. Stress applied to that material. Okay, so compressive, tensile, another really important one. Is when we talk about geologic materials, we're often interested in their shear strength. And shear strength is the ability to resist shearing or sliding of material. And so shear, compressive is this, tensile is this apart, and shear is that sliding of material. And so this is really important, quantifying the strength of, say, a pile of sand. How steep can we make that pile of sand before it's too steep, and then the stress is greater than the strength of the material and it collapses. So that brings us to a really, really important concept in understanding hill slopes, and that's the concept of the angle of repose. So the angle of repose is the steepest gradient that we can make a material based on the strength. And so here, right here on the slide, this angle right here, ooh, that's tough. There we go. That's our angle of repose, that I can't stack up the sand any steeper on this hill slope. If I stack it up any steeper, it's just going to slide down. Okay, so that's our angle of repose, and that's based on the shear strength of the material. How much can it resist sliding down the slope? Does that make sense? And so what is that shear strength going to be based on? Well, it's going to be based on the characteristics of the material, right? Imagine you have all those little bits of sand, and all those little bits of sand are interlocking on each other. I don't have an example here. Here's two bits of sand, and so how they're sitting and connected and the friction between them is what's going to determine that shear strength. Okay, we can more quantitatively define the shear strength, and so this is the equation we use to define shear strength. We got a couple variables here that we need to define. So the shear strength of the material, SS, is going to be equal to the cohesion plus the effective normal stress multiplied by the tangent of the angle of internal friction. Okay, so we're going to talk about what all these are. Cohesion is how sticky the material is. How much does it stick to itself? And so sand, sand isn't particularly cohesive, right? It doesn't stick to itself very much compared to, say, like a sticky clay or like bedrock, right? Bedrock would have a lot of cohesion to it. It's really sticky. Those bonds, those bonds in the silica atoms are very strong, and so you've got a very cohesive material. Okay, our next term here is our effective normal stress. So an effective normal stress is essentially the force that's going to be perpendicular to the hill slope. So this is our, here's my finger, there we go. That's going to be perpendicular to the slope. That's our normal stress. And so essentially this is going to be related to the force of gravity acting on our slope. And finally, our last term here is our angle of internal friction, phi, and that describes essentially how shear strength varies with normal stress. As the normal stress varies, how does our strength vary of the material? Oftentimes, it's easy to understand this thinking about something called Coulomb's equation. So this is Coulomb's equation right here. And in Coulomb's equation, what we're doing is we're thinking about the strength of a material relative to that shear strength, how much it's resisting deformation as a function of normal stress. Normal stress. So here we've got a material that is going to have a certain amount of strength even with minimal normal stress, and that's associated with the cohesion of the material. And then as we start increasing the normal stress, we're going to increase the shear strength of the material. The materials that have higher normal stresses have higher shear strength. Now, the variation in how much it increases or decreases the shear strength with normal stress is associated with that angle of internal friction. That's going to tell you how steep your line is, and that's going to vary based on the material. But what does this mean? Well, what this is telling us is that if we have a pile of sand, or we have a slope, and depending on the angle of that slope, we're going to have a different strength of our material, right? Because if we've got a flat slope, we've got a lot of gravity acting on that slope, pulling it down and holding it in place. So in that case, we'd be over here, we'd have a really high normal stress and a high strength of the material. But as we increase that, that slope of the material, we're going to have less and less gravity that's pulling the material straight down and holding it flat in place. And then we're going to be in that slope position, and we're going to be decreasing that shear strength of the material. Okay, so if we think about the difference in some common materials, we can think about the difference between the shear strength of sand versus clay. So as I mentioned, sand isn't particularly cohesive, and so we start here with no cohesion, and then as we increase that normal stress, we increase that shear strength of the material. Clay, on the other hand, is sticky. So it has a certain amount of strength even if you have no normal stress. But then as you increase the normal stress, we have a lower angle of internal friction in clays, and you don't have as great of an increase in the shear strength relative to the increase in the normal stress. So great. Shear strength in clays versus sand. Okay. The final point here is that cohesion is really, really important for understanding how you can get a nice slopey hill slope like this versus almost a steep vertical cliff. Bedrock has very, very high values of cohesion relative to sand, and so you can make very, very steep slopes in bedrock. There's a nice table in your textbook that shows kind of the typical strength in terms of those friction angles and the cohesion. So kind of a sandy soil here is going to have almost no cohesion and have a higher friction angle than, say, a clay, but a clay is going to have some cohesion to it. And these are measured in our cohesion values in kilopascals here. Okay, going down below here, look at our rocks here. Our intact rock, we're going to have orders of magnitude higher amounts of cohesion. So rocks have much, much higher cohesion. All right, that's all I got for you on hill slope form. Next, we're going to be moving on, and we'll be talking about types of mass movements. So enjoy. I hope you enjoyed our first discussion of colluvium and hill slopes, and we'll be back for more soon. Thank you.